Hi everyone, today we're going to go over lesson 7-1, graphing exponential functions. So we're going to have some new vocabulary you might hear as an exponential function, exponential growth, asymptote, growth factor, decay factor, exponential decay, and just some of the words you might hear that will pop up in this lesson possibly. So to start off here is the parent function of exponential growth. So as we can see, it's going up and to the right. This is b to the x, where b is greater than 1. It is continuous, 1 to 1, and increasing. The domain is all real numbers. My range is all positive real numbers. And then my asymptote is on the x-axis, meaning I'm not actually going to cross it. I'm going to get really close to it, but not touch it. And then I have an intercept at 0, 1, so I do have a y-intercept. Go ahead and pause the video if you need more time to take notes. So our first example is graph y equals 4 to the x and then state the domain and range. So here they have making a table of values, and you can do this with or without a calculator. You should be able to do the negative exponents by using the negative exponent property, but those are our values. Next, we would go ahead and plot them, and this is what our graph would look like. The domain is all real numbers, and the range is from 0 to infinity. So go ahead and pause the video, take a chance to go ahead and graph this and see if you can match the correct graph. All right, by using a calculator or just plotting some points, such as, when x is 2, you should get 9 and have kind of an idea of where things are, you should get C. Looking at transformations, we have A, H, and K. Same as they've always been. H is horizontal translation, K is vertical translation, and then A is my orientation and shape. Remember, if A is negative, the only thing that tells me is it's upside down. After that point, you ignore the negative and then look at the absolute value of A to determine if you have growth or compression or a stretch. So here we have graph the function y equals 3 to the x minus 2, state the domain and range. So we can go ahead and do this by hand, and we get some numbers that we can go ahead and plot. So we plot our points, and we get that the domain is all real numbers. My range is from -2 to infinity. And as always, again, pause the video if you need more time. Here we have y equals 2 to the x minus 1. We're going to state the domain and range. You get some coordinate points for us to plot. So this is what our graph looks like. And here we would say that, again, our domain is all real numbers. Our range this time is from 0 to infinity. All right, go ahead, take a moment to graph y equals 2 to the x minus 4 and match to the corresponding answer. All right, you should get C. One hint we do have here is this -4 should have told you that your asymptote is now down here. It's a hint that we do have. So now we have graphed the function y equals x to the minus 2 plus 3. So I'll give you a moment to go ahead and do this one. All right, by graphing it, or if you know that we have this plus 3 here, so that tells me that I have an asymptote at y equals 3. So we do get A. Next example theory we have, in 2006, there was 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing at 19.5% annually. Draw a graph showing how the number of users would grow from 2006 to 2016 if that rate continued. So when we talk about rates, we always talk about rates as a decimal. So we do need to go ahead and change this. And always, when in doubt, take your percent, divide it by 100, and that will get you your decimal. So in this case, our rate is 0.195. And we're going to say 1.020 in billions. The fact that we say in billions is how we're measuring allows us not to have to use this huge number here. So we can go ahead and write our equation. To get our equation, you would do 1 plus the rate on the inside the parentheses. And this is specifically for growth. You would do 1 plus. If it was decay, you would do 1 minus. So they simplify it. We're then going to go ahead and graph it. Your starting point year would be 2006, so then you would move forward. If you want to relabel this, you can say years since 2006, and you can do 0, 1, 2, 3, 4, 5, 6 in that way. But this is what it would look like, and says we'd have about 6 billion people using the internet. All right, so go ahead and try this one. In 2006, there were about 2 billion people worldwide using cell phones. At that time, the number of users was growing by 11% annually. Which graph shows how the number of users would grow from 2006 to 2014 if the rate continued? All right, so what we should go ahead and graph would be my original amount was 2, and we're saying in billions, so I don't need to actually do anything else. So I can do 2.0 if I wanted, and I'd do 1 plus 0.11 to the t or x power. And I actually would just graph this. I wouldn't have to worry about it. And by doing that, you should get d. All right, next we're going to take a look at the exponential decay. It's almost exactly the same. The only difference is that it's going down and to the right instead of up. This happens when your b value is still a positive number, but it is between 0 and 1. So it's continuous, 1 to 1, and decreasing. It has a domain of all real numbers. My range is all positive y values, and my asymptote's at the x-axis, so at y equals 0, and my intercept's still 0, 1. So very much the same. The only difference is it's a decreasing graph instead of increasing. So we're going to do about the same stuff we did earlier. So we are going to state our domain and range. We get our points. So they just used a couple different ones. We would plot our points, and this is what our graph would look like. So our domain is all real numbers, and y is greater than 0. So next we have graph the function y equals -4 times 1/2 to the x minus 1 plus 2. So we have some transformations here. The negative sign tells us it's upside down. 4 tells us it's stretched vertically. Remember, the pattern is x minus h, so x minus 1 means h is positive 1. So it translates to the right 1 unit. K is 2, so it goes up 2 units. So this is what our graph would look like. Our domain is still all real numbers. Our range now, notice the range value is always going to follow with the k value. So it's always going to be greater or less than the k value. So in this case, all values less than 2 is my range. All right, go ahead, pause the video to graph y equals 1/2 to the x. All right, you should get A when you graph that. All right, go ahead and pause the video so you have a chance to go ahead and graph y equals -6 times 1/3 to the x minus 2 minus 3. All right, with graphing, you should get A. So next we're going to look at real-world exponential decay. So the pressure of the atmosphere is 14.7 pounds per inches squared. At Earth's surface, it decreases by about 20% for each mile of altitude up to about 50 miles. Draw a graph to represent the atmospheric pressure for altitude from 0 to 50. So here they gave us the pattern that we need, or a formula, A times 1 minus r to the t power. A is going to be my starting point or initial value. R is my rate as a decimal, and t is time in years. or in this case, miles. So here we have 14.7 times 0.8. Anytime you see less than 1 in the parentheses, that tells you it's a decay function. So we're going to head and graph, and we can see that it is decreasing. Next, we want to estimate the atmospheric pressure at an altitude of 10 miles. So we'd take our formula and we would just plug in 10 for T, and we would get about 1.58 pounds per inches squared by using the calculator. So they said you can kind of do 1.58, you can do 1.6. It just depends on the rounding that they are asking specifically for you to do. So here is a problem for you to go ahead and try. Draw the graph to represent the air pressure for a trip from 0 to 40 miles given the information. All right, you should get B. One thing you're going to use, your formula should have been y equals 34.7. 1 minus 0.03 to the t power or to the x power, whichever one you want to use. When you're graphing it on a calculator, you would have to use x. And again, the calculator will graph it without you simplifying it. If that is where you have an issue, don't worry about simplifying it. So using the same information, what is the air pressure after about 20 miles? Pause the video to give yourself a chance. All right, so we would take 34.7 times 1 minus 0.03 to the 20th mile. When we do that, you should get D 18.87. So that is the end of lesson 7-1. I will see you next time.